Hello, everyone. Welcome back. We are up to lesson 10 now of Unit 7. No new lesson notes, so we're going to go right into the examples here. So let's take a look at this example. So, a biologist is breeding fruit flies to include a specific genetic mutation that will be useful in understanding memories in humans. To check whether a fly has the mutation, a DNA sequence is analyzed in a way that kills the fly. So the biologist only wants to test a sample of the flies to estimate the proportion of flies that have the mutation. The biologist selects 40 flies to sequence at random and finds that 9 of them have the genetic mutation. Based on this sample, number one, estimate the proportion of flies in this group that has the genetic mutation. So what we're going to do is there's 40 flies in this group, 9 of them have the mutation. So to estimate the proportion, we're simply going to do 9 divided by 40. So I'm just going to divide that using the calculator on my phone. And I'm getting 0.225. Okay, so 22.5%. Okay. The scientist is worried that only having one sample may not be reliable for estimating the proportion of flies with the mutation, but does not want to sacrifice more flies to get a larger sample. The proportion from the sample is a good estimate for the population proportion, but is difficult to understand the possible variability from a single value. Andre has a suggestion for how to better understand the variability. A. Assume the sample is representative of the population of flies and create a simulation that mimics what the scientists found. Andre gets 200 pieces of paper and marks 45 of them as mutant and puts them all in a bag. Since Andre decided to use 200 pieces of paper, why should 45 of them be marked mutant? And what are some other combinations of total number of pieces of paper and number marked mutant that he could use? So the key is he chose 45 out of 200 to be marked mutant. Well, in our sample, we had 9 out of 40. The question is, are these two fractions related? Are these two fractions related? Well, it turns out if I multiply 9 times 5, I get 45, right? And if I multiply 40 also times 5, I get 200. So 9 out of 40 and 45 out of 200 are equivalent. So that's why this works. So to answer the second part of the question, what are some other combinations? Well, in this case, I multiplied numerator and denominator by 5. I could multiply it by any number. So I could do, say, 18 out of 80 if I multiply numerator and denominator by 2. Okay, I could do, let's see, I could do 27 out of 120. Okay, that would be multiplying numerator and denominator by 3. 9 times 3 is 27. 40 times 3 is 120. I could also do 36 out of 160. Because 9 times 4 is 36 and 40 times 4 is 160. And it can go on and on from there, okay? But those are some other combinations that we could use. Those are all equivalent to 9 out of 40, okay? Part B. Andre then simulates the scientist's sample by drawing a slip of paper from the bag, noting whether it is mutant or not. Then replacing the paper into the bag and drawing another paper until he has a sample of 40. He repeats this process for 50 trials and creates a dot plot showing the proportions that include showing the proportion that are mutant from each trial. Estimate values on the dot plot a range of proportions that include about 95% of the proportions from the trial. Okay, 95%. So the key in this case is he does 50 trials. Okay, so I want a middle interval that includes 95% of them. So if I were, and let me do a different color here, if I were to say take that one out and that one out and take these two out, so that would be taking 4 out, that would be 46 out of 50, and 46 out of 50 is 92%, which is pretty darn close. To 95. Now, if I were to say put these two back in, that would bring me to 48 out of 50. Okay, and 48 out of 50, if I divide that out, okay, is 96%. So, again, close to 95. So a good estimate of how much contains the middle 95% would be this part right here, which would be from 0.1 to 0.3. So 0.1 to 0.3. Okay, so that would be 0.1 would be 10%, 0.3 would be 30%. Okay, so there's B. C. Andre then finds the mean proportion from his simulations to be 0.2195 and the standard deviation to be 0.06. Okay, how far are your values from the last question from the mean? This will represent the estimated margin of error. So remember in the last lesson, if you look back at the previous lesson's lesson notes, I talked about we can estimate the margin of error by doing 2 times the standard deviation. So in this case, that would be 2 times 0.06, which is 0.12 or 12%. Okay? So how far are your values from the last question from the mean? This will represent your estimated margin of error. That would be 0.12. Okay, because we can estimate the margin of error by simply doubling the standard deviation. Okay, and then D. Divide the distance from the last question by the standard deviation to get the margin of error in terms of number of standard deviations. So my answer from the last question was 0.12. Okay. My standard deviation is 0.06, which gives me 2 standard deviations. Okay. 2 standard deviations. And we know that 95% of the data is within 2 standard deviations of the mean. Again, from our previous lessons, lesson notes, when we're talking about normal distributions. Okay. And then to finish this off, number 3, based on Andre's simulations, should the scientists feel confident that the proportion of flies is within 2 standard deviations of the mean for the simulations? We just answered that. The answer in this case is yes, because we estimated our margin of error, okay, and that gave us 2 standard deviations. And I know that 2 standard deviations is 2 standard deviations represents 95% of the data. So all of this kind of goes together. So he should feel confident that the proportion of flies within 2 standard deviations of the mean for these simulations. Okay, and that is it for this lesson.